The material world is governed by the laws of entropy, a universal drive toward decay and disorder, where iron succumbs to oxidation, silver tarnishes in the presence of sulfur, and even the most resilient polymers eventually break down under the relentless assault of ultraviolet radiation. Yet, held within a human hand, a simple gold coin or a wedding band represents a profound defiance of these fundamental principles, maintaining its lustrous, unblemished surface for millennia without the slightest hint of chemical degradation. This yellow metal, known scientifically as element 79, occupies a unique position in the periodic table, not merely because of its scarcity or its historical role as a medium of exchange, but because of its extraordinary physical properties that make the modern digital age possible.
While the average individual perceives gold as a symbol of wealth or an aesthetic choice for jewelry, its true value lies in its role as an indispensable technological cornerstone, a material so stable and conductive that it functions as the very nervous system of the global telecommunications infrastructure. Without the unique atomic characteristics of gold, the device used to view this information, whether a high-performance computer or a compact smartphone, would be plagued by signal degradation, rapid hardware failure, and an inability to process data at the speeds required for contemporary civilization. The sheer permanence of gold is a result of its status as a noble metal, a term used in chemistry to describe elements that exhibit an almost total lack of reactivity under standard environmental conditions. From a purely scientific perspective, gold is the most non-reactive of all metallic elements. It does not combine with oxygen to form oxides, nor does it react with most acids or bases found in nature. This chemical inertness ensures that a gold artifact recovered from a sunken galleon after 500 years on the ocean floor will emerge with the same brilliance it possessed the day it was forged, requiring nothing more than a simple rinse to restore its original luster. This property of unchanging stability is what allows gold to serve as the critical interface in high-frequency electronic circuits, where the slightest layer of corrosion on a copper or silver contact would increase resistance and lead to system failure. Every high-end processor and every intricate circuit board relies on gold-plated connectors to maintain flawless electrical continuity over decades of use, ensuring that the pulses of data defining the modern world remain uninterrupted by the passage of time. Beyond its chemical resilience, gold possesses physical attributes that border on the surreal, challenging the standard understanding of how solids behave under mechanical stress. It is recognized as the most malleable and ductile of all known elements, a characteristic that allows it to be manipulated to a degree that seems to defy the constraints of material science. To understand the scale of this property, one must observe that a single gram of gold, a fragment roughly the size of a single grain of rice, possesses the structural integrity to be drawn into a continuous, unbroken wire extending for nearly 3,000 meters. This wire, thinner than a human hair, remains capable of conducting electricity, making it an ideal component for the microscopic bond wires that connect integrated circuits to their external packaging. Furthermore, the malleability of gold allows it to be hammered into sheets of such extreme thinness that they are referred to as gold leaf, reaching a depth of approximately 100 nanometers. At this thickness, gold undergoes a fascinating transition. It becomes semi-transparent. When held up to a light source, these ultra-thin gold sheets allow a soft green light to pass through them, while simultaneously reflecting the vast majority of infrared and ultraviolet radiation. This specific optical behavior is not merely a laboratory curiosity. It is a vital functional requirement for the visors of extravehicular activity suits worn by astronauts, where a layer of gold thinner than a virus serves as a transparent shield against the blinding, unshielded radiation of the sun. The presence of gold in a modern household is far more pervasive than many realize, extending well beyond the confines of a jewelry box. In every high-speed internet connection, every satellite relaying global positioning data, and every medical diagnostic tool used to detect complex diseases,
Gold is the silent facilitator of precision. The metal's density, combined with its conductivity and immunity to environmental factors, makes it the only viable choice for the critical points of failure in complex machinery. While other metals may be more abundant or less expensive, they lack the multifaceted utility that defines element 79. The transition from utilizing gold as a decorative rarity to employing it as a foundational industrial resource represents a major shift in human technological evolution. It is a material that has dictated the flow of history, yet its most significant contributions are occurring now, in the silent pulses of electricity traveling through gold-plated contacts, and in the reflective surfaces of instruments peering into the farthest reaches of the cosmos. The narrative of gold is not a story of human greed, but a study of a material that bridges the gap between ancient craftsmanship and the future of interstellar exploration.
Before delving deeper into the violent cosmic origins of this extraordinary element and the way it has reshaped the trajectory of our species, please consider subscribing to this channel and engaging with the content by liking this video. Your participation assists in the continued production of high-quality scientific narratives that explore the hidden complexities of the physical world. Additionally, feel free to share in the comments which specific property of gold, its chemical immortality, its extreme malleability, or its role in modern electronics, challenges your existing perception of this metal the most. Such feedback is invaluable in refining our exploration of the materials that define the human experience. To comprehend the true nature of gold, one must look past its surface brilliance and examine the atomic structure that gives rise to its unique characteristics. Gold's atomic number is 79, placing it in the 6th period of the periodic table, a region where the electrons of heavy elements begin to exhibit what are known as relativistic effects. Because the nucleus of a gold atom contains 79 protons, it exerts a massive electromagnetic pull on the electrons orbiting it. This causes the innermost electrons to travel at a significant fraction of the speed of light, roughly half the speed of light, in fact. According to Einstein's theory of relativity, as an object's velocity increases toward the speed of light, its mass also increases. This increase in mass causes the orbits of the electrons to contract, pulling them closer to the nucleus. This contraction specifically affects the s orbitals and p orbitals, which in turn alters the way the atom absorbs and reflects light. This is the precise reason why gold possesses its distinctive yellow hue. While most metals reflect the entire visible spectrum and appear silver or white, the relativistic contraction in gold allows it to absorb blue light and reflects the red and yellow wavelengths. Without the influence of special relativity, gold would be indistinguishable in appearance from silver. This same atomic configuration is responsible for the metal's legendary lack of reactivity. The electrons are held so tightly by the nucleus and are so strategically arranged in their shells that gold has no quote, _0 __ to gain or lose electrons when coming into contact with other elements. In chemical terms, gold has a very high ionization energy and a low affinity for oxygen, meaning it requires an immense amount of energy to break its metallic bonds and form a compound. It is one of the few elements that can be found in nature in its quote, one state, pure, unalloyed, and metallic, rather than as part of an oxide or sulfide ore. This is why the gold found in ancient tombs or at the bottom of the ocean remains pristine. It is essentially chemically isolated from its environment, a characteristic that makes it the most reliable material for long-term storage of value and for the manufacturing of components that must last for decades without maintenance. The stability of gold is not an accident of nature. It is a direct consequence of the physics governing the behavior of matter at high atomic weights. In the realm of engineering, the malleability of gold is utilized to create surfaces that are perfectly smooth at the molecular level. When gold is deposited onto a substrate via a process known as physical vapor deposition, it forms a layer that is incredibly uniform and free of the microscopic pits and fissures
that characterize other metals. This makes gold the ideal coating for high-precision mirrors used in laser systems and infrared telescopes. In the aerospace industry, gold's ability to reflect 99% of infrared radiation makes it the most efficient thermal shield available. It is used to wrap sensitive components of satellites and lunar landers, protecting them from the extreme temperature fluctuations of space, which can swing from hundreds of degrees above zero in direct sunlight to hundreds of degrees below zero in the shade. The thin, shimmering foil seen on the Apollo lunar module and the modern Mars rovers is not for decoration. It is a high-performance, gold-based insulation system designed to ensure that delicate electronics do not overheat or freeze in the vacuum of the void. Furthermore, the role of gold in the biomedical field is expanding at a rapid pace, moving far beyond the traditional use of the metal in dentistry. Because gold is biologically inert, it does not provoke an immune response when introduced into the human body. This makes it an ideal material for implants, such as stents used to keep arteries open or gold weights used in the eyelids of patients with facial nerve paralysis. More recently, the development of gold nanoparticles has opened new frontiers in the treatment of cancer. These microscopic spheres of gold can be engineered to accumulate specifically within tumor tissues. When exposed to certain frequencies of light or infrared radiation, the gold particles absorb the energy and convert it into heat, effectively destroying the cancerous cells from the within while leaving the surrounding healthy tissue unharmed. This level of precision is only possible because of gold's unique electronic properties and its total lack of toxicity. As we examine the objects in our daily lives, from the SIM card in a phone to the coating on a high-end connector, we are seeing a material that has been shaped by the most extreme forces in the universe. Gold is not merely a commodity, it is a fundamental building block of technological progress. It is a substance that has transitioned from being a symbol of divine power in the ancient world to being a literal component of our most advanced scientific achievements. The properties that once made it the flesh of the gods now make it the blood of the machine. The journey of gold from the heart of a dying star to the circuit board of a modern computer is a testament to the metal's enduring utility and its indispensable role in the architecture of the future. Understanding gold requires a shift in perspective, from seeing it as a static hoard of wealth to recognizing it as a dynamic and vital participant in the ongoing story of human innovation. Every milligram of this metal in our pocket is a tiny piece of cosmic history, a material that has survived billions of years to ensure that our digital world remains functional and our exploration of the universe continues unabated. The genesis of gold is a narrative that transcends the boundaries of our planet, requiring a journey into the most violent and energetic phenomena documented in the field of astrophysics. While many elements on the periodic table are the products of standard stellar nucleosynthesis, the process by which stars fuse lighter nuclei into heavier ones, gold occupies a category of elements whose creation necessitates conditions far more extreme than those found in the core of a typical sun. In the standard life cycle of a star, nuclear fusion proceeds until it reaches the production of iron. Because the fusion of iron consumes more energy than it releases, the process halts, leading to the gravitational collapse of the stellar core and a subsequent supernova explosion. However, even the colossal energy of a supernova is insufficient to produce the abundance of heavy elements like gold, platinum, and uranium observed in the universe. Scientific consensus, bolstered by recent gravitational wave observations, points to a much rarer and more cataclysmic event: the collision and merger of two neutron stars. A neutron star is the ultra-dense remnant of a collapsed massive star, a sphere roughly the size of a city but containing more mass than our Sun. When two such objects, locked in a binary orbit, finally spiral inward and collide, the resulting explosion is known as a kilonova. During this brief, intense event, matter is subjected to an environment of unimaginable temperature and pressure, triggering what is known as the R process, or rapid neutron capture. In this fraction of a second,
atomic nuclei are bombarded by a high flux of neutrons so intense that they grow into heavy, unstable isotopes before they have the chance to decay. As these isotopes eventually stabilize, they transform into the heavy elements that eventually populate the cosmos, including gold. Every atom of gold present on Earth today was forged in these distant cosmic crucibles, ejected into space at significant fractions of the speed of light, and eventually incorporated into the vast clouds of gas and dust that would coalesce to form our solar system roughly 4.5 billion years ago. The presence of gold on the surface of the Earth presents a significant geological paradox that was only resolved through the study of early planetary evolution. During the Hadean Eon, the newly formed Earth was a molten, incandescent sphere of rock and metal. As the planet underwent differentiation, gravity caused the densest materials to migrate toward the center, while lighter silicates rose to form the mantle and crust. Gold is chemically classified as a siderophile, or an __4__ element, meaning it dissolves readily in molten iron. Consequently, as the Earth's massive iron core formed and sank, it acted as a gravitational sieve, dragging virtually all of the planet's original gold supply, along with other precious metals like platinum and palladium, deep into the interior. Calculations suggest that the Earth's core contains enough gold to cover the entire surface of the planet in a layer roughly half a meter thick. However, this vast reservoir is entirely inaccessible, locked away under thousands of kilometers of high-pressure rock. The gold that humanity has mined throughout history, and the gold that exists within the modern economy, should theoretically not be here. Its existence in the Earth's crust is the result of a secondary cosmic event known as the Late Heavy Bombardment. Approximately 3.8 to 4.1 billion years ago, long after the Earth's crust had solidified and the core had sequestered the original heavy elements, the inner solar system was subjected to a massive influx of comets and asteroids. These metallic bolides, many of which were rich in precious metals that had not been subjected to planetary differentiation, impacted the Earth's surface, depositing a fresh layer of gold and other siderophiles into the lithosphere. This late veneer of extraterrestrial material is the primary source of all accessible gold. In a very literal sense, the gold found in terrestrial veins is an alien resource, a cosmic afterthought delivered to the planet's surface by a rain of fire that lasted millions of years. The distribution of this gold within the Earth's crust is exceptionally sparse, reflecting its status as one of the rarest elements in the universe. On average, the concentration of gold in the crust is approximately 4 parts per billion. To visualize the scarcity of this material, one must consider that if all the gold ever mined in human history, estimated to be around 200,000 metric tons, were melted into a single solid cube, it would measure only 21 meters on each side. This entire mass would fit comfortably beneath the arches of the Eiffel Tower or within the footprint of a large residential building. This extreme rarity is what has historically dictated the metal's value, but it is also what makes the geological processes that concentrate gold so vital to the advancement of technology. For gold to become accessible for human extraction, specific geological mechanisms must occur to concentrate these scattered atoms into localized deposits. This process is driven primarily by hydrothermal activity. Deep within the crust, water heated by the Earth's internal energy becomes highly pressurized and chemically enriched. This supercritical fluid is capable of dissolving trace amounts of gold from the surrounding rock. As the fluid migrates through fractures and faults toward the surface, it encounters lower pressures and cooler temperatures, causing the gold to precipitate out of the solution and accumulate in quartz veins. This tectonic plumbing system is what has created the world's great gold provinces, such as the Witwatersrand Basin in South Africa or the Carlin Trend in Nevada. Without the continuous churning of the Earth's tectonic plates and the circulation of mineral-rich fluids, The gold delivered by ancient meteorites would remain so thinly dispersed that its extraction for industrial or economic purposes would be physically impossible. The study of gold's distribution also reveals fascinating insights into the age of the Earth's geological features. Many of the most productive gold deposits are found in quote, _6__, which are remnants of ancient volcanic and sedimentary rocks dating back to the Archean eon, over 2.5 billion years ago. These regions represent the skeletal remains of the earliest continents. Because gold is chemically inert and physically durable, it can survive through multiple cycles of erosion and sedimentation. This leads to the formation of placer deposits, where gold particles are washed into riverbeds and concentrated by the action of water, a process that fueled the great gold rushes of the 19th century. The durability of gold ensures that an atom mined today from an ancient riverbed is the exact same atom that was delivered to the Earth by a meteorite 4 billion years ago, and forged in a neutron star collision billions of years before that.
The isotope analysis of gold further confirms its unique cosmic heritage. Unlike many other elements, gold has only one stable isotope, gold-197. This lack of isotopic variety is a hallmark of the specific R-process nucleosynthesis that occurs during kilonovae. When scientists analyze the composition of meteorites, particularly carbonaceous chondrites, they find a chemical signature that matches the distribution of gold and other heavy elements in the Earth's crust, providing an empirical bridge between the minerals we extract and the celestial events that produce them. The consistency of these findings across the fields of geology, chemistry, and astrophysics reinforces the understanding that the materials integrated into our daily lives are products of a vast, interconnected cosmic history. The concentration of gold in the oceans is another area of scientific interest, though it highlights the difficulty of extracting the element when it is not concentrated by geological forces. It is estimated that the world's oceans contain approximately 20 million tons of gold, held in a highly dilute solution of roughly 13 billionths of a gram per liter. While the total volume is massive, the energy required to process the water and extract the metal far exceeds the market value of the gold itself. This serves as a stark reminder of the unique conditions required to make this element useful to civilization. Gold is not merely a substance that is found. It is a substance that must be concentrated by the specific heat and pressure of the Earth's interior over millions of years to become a viable resource for the development of advanced technology. The relationship between the Earth's magnetic field and its metallic core also plays a subtle role in the story of gold. The movement of molten iron in the outer core creates the magnetosphere, which protects the atmosphere and the surface from solar radiation. While gold is not magnetic, its sequestered presence in the core alongside iron and nickel is a reminder of the planet's violent beginnings. The fact that any gold remains in the crust at all is a geological accident, a consequence of the timing of the late heavy bombardment. Had those meteorites arrived earlier, while the planet was still entirely molten, the gold we use today would have followed the original supply into the core, leaving the surface of the Earth devoid of the material necessary for the eventual creation of microelectronics and high-precision scientific instruments. Every piece of gold utilized in contemporary society, from the thin wires in a microprocessor to the reflective coating on a telescope mirror, is an artifact of these three stages of cosmic and planetary evolution. Synthesis in a kilonova, delivery via an asteroid bombardment, and concentration by hydrothermal systems. This metal is an enduring witness to the history of the universe. Its atoms are indestructible under normal conditions, meaning that the gold currently moving through the global economy has a lineage that stretches back to the very dawn of the solar system. The sheer scale of time and the intensity of the forces involved in creating gold elevate it from a simple commodity to a fundamental component of the universe's material narrative. When we utilize gold in our technology, we are not just using a metal, we are employing a substance that required the death of stars and the bombardment of a young planet to reach our hands. The stability of gold's atomic structure
means it does not undergo radioactive decay, nor does it easily form compounds that would alter its state. This makes it a unique constant in an ever-changing environment. While the carbon in our bodies is constantly recycled through the biosphere, and the iron in our infrastructure eventually turns to rust, gold remains unchanged. It is a material that exists outside the standard cycle of terrestrial decay. This permanence, combined with its extraordinary origins, is why gold has been regarded with such reverence throughout human history. However, as our understanding of physics and geology has deepened, the ore once reserved for its aesthetic beauty has been replaced by an intellectual appreciation for its physical properties. We now recognize that gold's value is not a social construct, but a reflection of its unique place in the periodic table and its indispensable role in the technical architecture of our species.
The journey of gold from the heart of a neutron star merger to the crust of the Earth is a testament to the complex, high-energy processes that define the material reality of our existence. The human relationship with gold is an ancient dialogue between the immutable laws of physics and the evolving structures of human civilization. While its cosmic origins and atomic stability define its physical reality, the historical trajectory of gold is a testament to how a single material can catalyze the development of global economics, the advancement of scientific methodology, and the expansion of geographical knowledge. In the ancient world, the perception of gold was intrinsically linked to its immunity to decay, a property that immediately elevated it above all other substances available to early metallurgy.
For the civilizations of the Nile Valley, specifically during the dynastic periods of ancient Egypt, gold was not initially conceived as a currency, but as a physical manifestation of the divine.
Known as the flesh of the gods, particularly associated with the sun god Ra, gold's brilliant yellow luster and its refusal to tarnish or corrode suggested a material that existed outside the standard cycle of birth and death. This was a sophisticated, if mythological, observation of the metal's noble status. The Egyptians recognized that while copper would turn green and silver would blacken, gold remained constant, an island of permanence in a world of entropy. This perceived divinity led to the development of highly advanced metallurgical techniques thousands of years before the formalization of modern chemistry. The artisans of the Old Kingdom mastered the art of alloying gold with silver to create electrum, and they pioneered the process of fire assaying to determine the purity of the metal. These early chemical experiments were driven by the need to ensure that the flesh of the gods was not corrupted by baser metals.
The psychological impact of gold's permanence cannot be overstated. It provided a visual and tactile representation of eternity, which in turn dictated the architecture of their funerary rites and the construction of their most sacred monuments. The sheer volume of gold recovered from the tomb of Tutankhamun, totaling over 100 kilograms of pure metal, was not merely a display of wealth, but a functional technological investment intended to preserve the essence of the deceased through the perceived incorruptibility of element 79. As human society has transitioned from ritualistic structures to complex trade networks, the physical properties of gold, specifically its density and malleability, transformed it into the world's first universal medium of exchange.
The shift from gold as a divine substance to gold as a monetary standard was a logical progression based on the metal's unique material profile. Because gold is incredibly dense, it allows for a high concentration of value in a small, portable volume. Because it is chemically inert, it does not lose mass over time through oxidation, ensuring that a coin minted in one century retains its exact physical weight in the next. This reliability provided the foundation for the first globalized economies. The Lydians, in the 7th century BCE, were the first to standardize this by minting coins of a consistent weight and purity, effectively creating a, quote, 9 for the software of human commerce. This development allowed for the accumulation of capital
and the funding of large-scale infrastructure projects that defined the classical world. The pursuit of gold served as the primary engine for the Age of Discovery, a period that reshaped the map of the world and facilitated the first truly global exchange of ideas, technologies, and biological species. The voyages of Christopher Columbus, Vasco da Gama, and Ferdinand Magellan were underpinned by the economic necessity of finding direct routes to the gold-rich regions of the East. The Portuguese and Spanish empires were not merely exploring for the sake of curiosity. They were engaged in a massive logistical operation to bypass the traditional Silk Roads and secure a steady supply of the one material that could fund their standing armies and bureaucratic machines. The influx of gold and silver from the New World into Europe in the 16th century triggered a phenomenon known as the price revolution, illustrating for the first time the complex relationship between mineral supply and inflationary economics. The massive redistribution of gold during this era acted as a catalyst for the rise of modern banking and the transition from feudalism to a proto-capitalist global system. The density of gold meant that it was the only substance that could be efficiently transported across oceans to settle international debts, making it the literal ballast of the global economy. Parallel to the geopolitical expansion driven by gold was an internal intellectual expansion led by the alchemists. For over a millennium, alchemy was the dominant framework for understanding the nature of matter, and its central obsession was the quote, 10 or the transmutation of base metals into gold. While modern science often dismisses alchemy as a pursuit of the impossible, it was in fact the cradle of modern chemistry.
The alchemical focus on gold was based on the observation that it was the quote, 11 metal, the most stable, the most beautiful, and the most resilient. Alchemists reasoned that if they could understand the underlying principles that made gold so perfect, they could apply those principles to medicine and the human condition. In their tireless efforts to synthesize gold through chemical reactions, they developed the foundational tools of the laboratory: distillation, sublimation, and the creation of strong mineral acids. One of the most profound examples of this accidental progress occurred in the 17th century with the work of the German alchemist Hennig Brand. In his pursuit of the quote, 12 a substance believed to be capable of turning lead into gold, Brand experimented with thousands of liters of human urine, subjecting it to intense heat and distillation.
He did not find gold, but he did discover a substance that glowed in the dark and burst into flames when exposed to air. He had isolated phosphorus, the first element discovered since antiquity that was not a metal. This discovery was a turning point in human history. It proved that the systematic investigation of matter could reveal entirely new substances with properties previously unimagined. The search for gold, though a failure in its primary goal, provided the empirical data and the experimental mindset that would eventually lead to the periodic table and the birth of the scientific method. Gold was the bait that lured the human mind into the rigors of chemistry, forcing us to abandon mysticism in favor of measurable, repeatable evidence. The quest for gold also drove significant advancements in physics, most notably in the work of Archimedes of Syracuse. The famous quote, 13 moment, where Archimedes discovered the principle of buoyancy and displacement, was triggered by a problem concerning the purity of a gold crown.
The king of Syracuse suspected that his goldsmith had substituted silver for a portion of the gold, and he tasked Archimedes with proving the fraud without damaging the crown. By realizing that gold's unique density would displace a specific and unchangeable volume of water compared to an equal weight of silver, Archimedes established the foundation of hydrostatics. This was one of the first times in history where a material's intrinsic physical property was used as a definitive legal and scientific proof.
Gold's extreme density, nearly twice that of lead, made it the perfect subject for this breakthrough,
as its displacement profile was so distinct from any other common material. In the 19th century, the global .14 in California, Australia, and South Africa acted as massive demographic and technological accelerators. These events were not merely chaotic scrambles for wealth, they were industrial-scale operations that spurred the development of hydraulic mining, advanced geology, and the construction of transcontinental railroads. The sudden influx of hundreds of thousands of people into previously remote areas necessitated the rapid advancement of communication and transportation technologies. The telegraph and the steamship became essential tools for managing the flow of information and resources between the goldfields and the world's financial centers.
In South Africa, the discovery of the Witwatersrand gold deposits led to the development of deep-level mining technology, pushing the limits of human engineering miles below the Earth's surface, where temperatures and pressures mirror the hostile conditions of the deep crust. This era proved that the demand for gold could overcome any physical barrier, forcing humanity to innovate at a pace that changed the face of the planet. The historical role of gold as a stabilizer reached its zenith with the international gold standard of the late 19th and early 20th centuries. This was a period of unprecedented global economic integration, where the value of every major currency was fixed to a specific weight of gold. This system essentially turned the Earth's gold supply into a global source code for value, ensuring that international trade was conducted on a transparent and predictable basis.
While the gold standard eventually collapsed under the pressures of the world wars and the complexities of modern central banking, its legacy remains in the massive vaults of the world's central banks, which still hold over 35,000 metric tons of the metal. These reserves are not merely relics of a bygone era, they are a recognition of gold's unique status as a Tier 1 asset, a material that carries no counterparty risk, and whose value is derived not from a government's promise, but from its own immutable physical properties. The transition of gold from a divine skin to a global currency, and finally to a technological catalyst, represents a masterclass in human adaptation. Every major leap in our understanding of the physical world, from the principles of buoyancy to the discovery of new elements and the mastery of deep Earth engineering, has been tethered to our interaction with this specific element. Gold did not quote 17 to be sought after. Its atomic structure simply provided a set of properties that humans found irresistible and indispensable. The drama of human history is inextricably linked to the yellow metal, not because of its color, but because of its absolute refusal to change. It was the one constant in a world of shifting borders, collapsing empires, and evolving ideologies. The same permanence that made it the flesh of the gods in ancient Egypt eventually made it the foundation of the modern scientific and economic world, a silent witness to the rise and fall of civilizations, remaining as brilliant and heavy today as it was when it first emerged from the cosmic furnace of a dying star. In the contemporary era, the primary utility of gold has shifted from the visible displays of wealth to the invisible foundations of the digital and scientific infrastructure. While the aesthetic allure of the metal remains, its true significance lies in its unique electronic and optical properties, which are indispensable for the functioning of modern society. The most pervasive application of gold is found within the architecture of high-performance electronics. Every smartphone, tablet, and high-speed computer contains a specific, measured amount of gold that ensures the reliability of its internal circuitry. The reason for this reliance is not simply the metal's electrical conductivity. Silver and copper are, in fact, more conductive than gold, but rather its absolute chemical stability. In the microscopic environment of a microprocessor, where electrical traces are separated by only a few nanometers, the slightest hint of oxidation or corrosion would lead to an immediate failure of the device. Copper and silver, while efficient, react with the trace amounts of oxygen and moisture in the air,
forming non-conductive layers that increase electrical resistance and eventually break the circuit. Gold, being a noble metal, remains entirely inert. It provides a permanent low-resistance path for the flow of electrons, ensuring that the millions of operations performed by a processor every second occur without interruption over the lifespan of the hardware. The physical integration of gold into these devices occurs at a level of precision that mirrors the complexity of the materials themselves. Within a standard smartphone, gold is used in the _quote_18____, the incredibly thin threads that connect the silicon chip to its external package. These wires are often thinner than a human hair and are attached using ultrasonic welding, a process that relies on gold's extreme ductility to create a molecular bond between the metal and the semiconductor. Furthermore, the contact points of SIM cards and the charging ports of high-end electronics are plated with a thin layer of gold to prevent the wear and tear associated with repeated mechanical friction. This plating ensures that every time a device is plugged in or a network connection is established, the electrical contact is as clean and efficient as it was on the day the device left the factory. In an age where data is the most valuable commodity, gold serves as the physical guardian of that data, protecting the integrity of the signals that define our digital existence. Beyond the terrestrial confines of consumer electronics, gold plays a critical role in the exploration of the cosmos, functioning as a vital instrument in the most advanced telescopes ever constructed. The James Webb Space Telescope, situated nearly 1.5 million kilometers from Earth at the second Lagrange point, utilizes gold as its primary optical medium. The telescope's massive 6.5-meter primary mirror is composed of 18 hexagonal segments of beryllium, each coated with a layer of pure gold only 100 nanometers thick. This choice of material is dictated by the laws of thermodynamics and optics. The James Webb is an infrared telescope designed to detect the faint, heat-based signatures of the first stars and galaxies formed after the Big Bang. While silver reflects visible light exceptionally well, gold is nearly 99% reflective in the infrared spectrum. By using a gold coating, the telescope can capture the longest wavelengths of light that have been stretched across the expanding universe for 13 billion years. The total amount of gold used on the mirrors is approximately 48 grams, roughly the mass of a golf ball. Yet it is spread so thin that it covers an area of 25 square meters, enabling humanity to peer further back into the history of time than ever before possible. The protective qualities of gold are equally essential for the survival of human beings in the hostile environment of space. The visors of the extravehicular mobility units, the spacesuits worn by astronauts, are coated with a microscopic layer of gold.
This serves a dual purpose. It reflects the intense thermal radiation from the sun, preventing the interior of the helmet from overheating, and it filters out the high-energy ultraviolet radiation that would otherwise cause permanent damage to the astronaut's eyes. Because the gold layer is only a few atoms thick, it remains semi-transparent to the visible spectrum, allowing the astronaut to see clearly while being shielded from the invisible, destructive forces of solar radiation. This same principle is applied to the thermal blankets used to wrap satellites and interplanetary probes. These __quote_19__ blankets often feature gold-coated polyimide films that act as a sophisticated thermos, reflecting radiant heat away from sensitive electronic components in the vacuum of space, where traditional convective cooling is impossible. In the realm of medicine, gold has transitioned from an ancient curative myth to a high-precision tool for diagnostic and therapeutic intervention. This is primarily due to gold's biocompatibility. The human body does not recognize gold as a foreign threat, meaning it does not trigger an inflammatory or immune response. This lack of toxicity allows for the use of gold nanoparticles in the targeted delivery of pharmaceuticals. These nanoparticles, measuring only a few billionths of a meter in diameter, can be chemically quote, with specific molecules that seek out and bind to cancerous cells. Once the gold particles have accumulated within a tumor, they can be activated using a specific frequency of near-infrared light. Because gold nanoparticles are highly efficient at absorbing this light energy and converting it into localized heat, a phenomenon known as surface plasmon resonance, they can effectively incinerate cancer cells from the inside out without damaging the surrounding healthy tissue.
This level of molecular-scale surgery represents a profound leap in oncology, moving away from systemic treatments like chemotherapy toward localized, material-based solutions. The diagnostic applications of gold are equally transformative. The rapid antigen tests used globally for the detection of viruses, including the influenza and COVID-19 pathogens, rely on colloidal gold, suspensions of gold nanoparticles in liquid. These particles are engineered to change color or aggregate when they come into contact with specific viral proteins. The distinct red line that appears on a positive test result is, in fact, the visual accumulation of millions of gold nanoparticles. This application leverages gold's unique optical properties at the nanoscale, where the interaction between light and the metal's surface electrons produces a vivid color change that is easily detectable by the naked eye. In this context, gold acts as a biological sensor of unprecedented sensitivity, providing a low-cost, high-reliability diagnostic tool that can be used in the most remote regions of the planet.
In the aerospace and defense industries, gold's high density and resistance to high-temperature oxidation make it an essential component of jet engines and high-performance sensors. Gold-based brazing alloys are used to join components within the combustion chambers of turbines, where the temperatures can exceed 1,000 degrees Celsius. Unlike other alloys that would become brittle or oxidize under such conditions, gold maintains its structural integrity and its bond with the surrounding materials. This ensures the safety and efficiency of modern air travel, where engine failure is not an option. Furthermore, the infrared seekers used in heat-seeking missiles and the advanced sensors in autonomous vehicles rely on gold-coated optics to maintain clarity and accuracy in diverse environmental conditions. Whether it is navigating a self-driving car through a foggy street or guiding a spacecraft to a landing on Mars, the consistent, unreactive nature of gold provides the reliability required for the most demanding technical challenges. The field of quantum computing also relies on the unique characteristics of gold to achieve the extreme conditions necessary for quantum decoherence. In these systems, the quantum processors must be cooled to temperatures approaching absolute zero, colder than the deepest reaches of interstellar space. To maintain these temperatures, the dilution refrigerators used in quantum labs utilize gold-plated copper components. The gold prevents the copper from oxidizing, which would create a barrier to thermal conductivity, and ensures that the heat can be efficiently removed from the system. Additionally, the microscopic circuits that carry quantum information are often made of gold or gold alloys to minimize the electronic noise that could disrupt the fragile quantum states of the qubits. As we stand on the threshold of a new era in computational power, gold remains the material of choice for bridging the gap between classical physics and the quantum world. The integration of gold into these diverse fields highlights a fundamental truth about the material. Its value is not merely a product of human desire, but a direct result of its physical performance. There is no other element in the periodic table that combines such high electrical and thermal conductivity with such total chemical inertness and extreme malleability. While researchers continue to explore synthetic alternatives and carbon-based nanomaterials, gold remains the gold standard for reliability and precision. It is a material that has proven its worth through billions of years of cosmic history and thousands of years of human usage. Today, it is the silent, shining heart of the technological machine, an element that works tirelessly behind the scenes to facilitate the communication, exploration, and health of the global population. When we consider the role of gold in our lives, we must look beyond the jewelry and the bullion to see the microscopic wires and the golden mirrors that are, quite literally, building the future of our civilization. It is a material that has successfully transitioned from being a symbol of the sun to being the very tool we use to study the stars and the infinitesimal building blocks of life. Every time we send a message, capture an image of a distant galaxy, or undergo a sophisticated medical procedure, we are benefiting from the unique atomic arrangement of element 79, a cosmic gift that continues to propel human progress. The culmination of gold's journey on Earth is defined by a physical property that is arguably more profound than its conductivity or its rarity: its functional immortality. In the rigorous framework of thermodynamics, most materials are transitory, eventually succumbing to the relentless process of oxidation, erosion, or molecular breakdown.
Gold, however, exists in a state of perpetual preservation, as its atoms do not form stable bonds with oxygen or most environmental pollutants. This chemical defiance of time has created a phenomenon unique to element 79, the near-total conservation of every milligram ever extracted from the Earth's crust. It is estimated by mineralogists and economic historians that approximately 90% of all the gold ever mined throughout the entire history of human civilization remains in circulation today, albeit in constantly shifting forms. This reality transforms the global supply of gold into a vast, liquid archive of human history, where the material itself acts as a witness to the rise and fall of empires, the advancement of technology, and the personal lives of billions of individuals. The gold currently contained within a modern electronic component or a piece of contemporary jewelry is likely a composite of countless previous incarnations.
Because gold is so easily melted and refined without losing any of its intrinsic properties, it is subjected to a cycle of eternal recycling that is unmatched by any other industrial material. A gold atom present in a modern wedding band may have once been part of a ceremonial dagger in the Hittite Empire, a stamped coin in the Roman treasury, or a decorative filament in a Renaissance tapestry. This continuity is not merely a poetic abstraction, but a physical reality. When gold is recycled, the process removes all traces of its previous alloys and impurities, effectively quote, 21 the metal to its pure elemental state. Consequently, the gold in the hands of a modern consumer is indistinguishable from the gold that was first unearthed by Neolithic miners 5,000 years ago. The metal does not age, it does not degrade, and it does not lose its value through use. This makes gold the only truly closed-loop resource in the human economy, a substance that is never truly consumed, only borrowed for a time before it is reshaped for a new purpose. This process of perpetual reuse is now finding its most critical application in the field of urban mining. As the demand for gold in the telecommunications and computing industries continues to accelerate, the environmental and economic costs of traditional subterranean mining have made the recovery of gold from electronic waste a global priority. 1 metric ton of discarded circuit boards can contain up to 40 times the concentration of gold found in a metric ton of raw gold ore. The recovery process involves sophisticated chemical leaching and electrochemical refining, which allows the gold to be extracted from its electronic graveyard and returned to the manufacturing cycle with its original purity intact. This industrial cycle ensures that the gold used to facilitate a digital transaction today will likely be used to power a medical diagnostic tool or a satellite component in the next century. The atoms of element 79 are the ultimate nomads of the material world, moving through the infrastructure of civilization with a permanence that defies the obsolescence of the machines they inhabit. The existential significance of gold, however, extends far beyond the boundaries of the Earth's atmosphere. When humanity sought a medium to carry a message into the depths of interstellar space, the choice of material was dictated by the same noble properties that make gold indispensable to our electronics. On the exterior of the Voyager 1 and Voyager 2 spacecraft,
which were launched in 1977 and have now entered interstellar space, are the golden records. These 12-inch gold-plated copper discs contain sounds and images selected to portray the diversity of life and culture on Earth. The decision to use gold was a purely scientific one, based on the metal's resilience to the harsh environment of the cosmos.
In the vacuum of interstellar space, a record made of traditional materials would be subject to erosion from cosmic rays and microscopic dust particles over millions of years. A layer of pure gold, however, provides a protective shield that is essentially immune to the chemical and physical degradation that would destroy other forms of data storage. These gold-plated discs are designed to remain legible for at least 1 billion years. In this context, gold is acting as a temporal mirror, reflecting the existence of the human species across a span of time that exceeds the expected lifespan of our own civilization. Long after the structures of our cities have crumbled to dust and the records of our digital age have been erased by the passage of eons, these golden plates will continue to drift through the void, carrying the signature of humanity. The stability of the gold atoms ensures that the grooves of the record will remain precisely defined, capable of being decoded by any sufficiently advanced civilization that might encounter them in the distant future. Gold is the only material we possess that is capable of serving as a reliable courier across such vast temporal and spatial distances. It is our species' ultimate fingerprint, a shining testament to our existence that is physically engineered to outlast the planet itself. The scientific narrative of gold thus concludes with a shift from the local to the universal. We began by observing gold as a curious, non-reactive metal in a handheld device, but we must end by recognizing it as a fundamental constant of the universe. In the far-reaching timeline of the cosmos, gold is one of the few elements that will remain largely unchanged as the universe moves toward its eventual heat death. While lighter elements are consumed in the hearts of stars and radioactive elements decay into lead over millions of years, the stable isotopes of gold remain. If we were to project the history of our solar system into the distant future, the gold that was delivered to Earth by the late heavy bombardment will survive the expansion of the Sun into a red giant. Even as the Earth is consumed and its silicate rocks are vaporized, the gold atoms will be dispersed back into the solar nebula, returning to the cosmic cycle from which they were first forged, in a neutron star collision billions of years ago. This perspective reveals that gold is not merely a resource that we own or trade, but a material that we are temporarily managing. We are participants in a much larger cycle of matter and energy, using a substance that has traveled across the galaxy to facilitate our brief period of technological development. The value we assign to gold is often framed in terms of currency or status, but its true worth is its reliability. It is the one material that does not lie. It does not change its properties based on the environment, it does not fail under the stress of time, and it does not disappear. It is the anchor of the material world. When a scientist looks through a gold-coated telescope at a galaxy 13 billion light-years away, or when a doctor uses a gold nanoparticle to destroy a tumor, they are utilizing a precision that was built into the very structure of the atom during the birth of the universe. The story of gold is the story of the human struggle against entropy. We live in a universe that is constantly tearing things apart, breaking down complexity into simplicity, and turning order into chaos. Gold is the exception to this rule. It is a material that resists the universal drive toward decay. By integrating gold into our most vital technologies, we are essentially borrowing some of its immortality to ensure that our knowledge can be transmitted, our health can be preserved, and our voices can be heard across the stars. Whether it is resting in a vault, pulsating with data in a fiber optic relay, or drifting through the silence of interstellar space, gold remains the same, a pure, heavy, and luminous witness to the trajectory of life. It is the ultimate machine of time, a physical link that connects the violent explosions of ancient stars to the pocket of a modern human, and eventually,
to the silent, distant future where it will serve as the final evidence that we were here. Gold is not just a metal. It is the material soul of our technological ambition, an alien element that we have used to build a world that, like gold itself, aspires to be eternal.